Here's a scenario most campers have lived. You're out in the woods, temperatures have dropped hard, and someone says the same thing they always say. We need a bigger fire, so you pile on more wood. The bonfire grows, crackles, roars, and everyone shuffles backward because the heat on their faces is overwhelming. But their backs are still freezing. 3 hours later, half the group is shivering anyway, wondering why a fire the size of a small car isn't keeping them warm. The answer is physics. Specifically, it's two physics problems happening simultaneously that almost nobody in the outdoor recreation industry ever explains clearly. A bonfire isn't a bad fire because it's dangerous. It's a bad survival fire because it breaks the fundamental math of heat delivery to the human body in at least 3 separate ways. Tonight we're running the actual numbers. We're covering why combustion efficiency collapses as fire size increases, how radiant heat geometry works against anyone who builds a fire too large to approach, what directed oxygen delivery does to combustion temperature, why fuel shape matters more than fuel quantity, and the underground fire structure that sidesteps every thermodynamic problem we're about to discuss. By the time this is done, you'll never look at a pile of burning wood the same way again. The credibility anchor before we dive in. The United States Army Survival Manual, Field Manual 3-76, tells soldiers to keep fires small and well concentrated rather than building large ones. That guidance didn't come from campfire tradition. It came from applied thermodynamics. That reasoning has been in official field doctrine for decades, and almost nobody outside formal survival training ever heard the physics explained. That changes right now. Let's start with combustion because most people carry an incomplete mental model of fire that costs them real warmth. Wood combustion isn't a single event. It unfolds in 3 stages. Stage 1 is drying, where the wood sheds its stored moisture before the chemistry can go anywhere. That phase pulls energy out of the fire rather than adding to it. Stage 2 is thermal decomposition, where extreme heat breaks apart the wood's cellulose into burnable gases, methane, hydrogen, carbon monoxide. These compounds are the actual fuel. Stage 3 is where the payoff happens. Those gases ignite and react with oxygen, releasing heat and light. Almost all the energy your fire produces lives in that final stage. Here's the problem that compounds as a fire gets larger. A big bonfire generates enormous heat at its core, but the outer fuel layers never get hot enough to decompose consistently. What you end up with is a fire that performs well in certain spots and just smolders in others, throwing off thick smoke in the process. That smoke is not a side effect. It's potential heat abandoning your campsite in molecular form. Each gray column rising into the dark represents combustion that stalled halfway through because the oxygen delivery failed. A compact, tightly built fire positions all its fuel in the active burn envelope simultaneously. Every piece gets what it needs, when it needs it. The efficiency gap is enormous. Open fires typically convert 40 to 60% of their fuel into usable thermal energy. A well-configured small fire, properly oxygenated, pushes that number to 80 or 90%. At 90%, you're getting close to twice the heat per log compared to a bonfire running at half efficiency. That's the gap between staying warm and watching the night get colder. But here's the pushback most people have. Sure, the small fire is more efficient per log, but the bonfire has way more logs burning. Total output still wins, right? That's exactly where the radiant heat geometry problem dismantles that argument completely. A fire delivers energy to your body through 2 distinct pathways. Convection is the movement of heated air through the surrounding space. Radiation is invisible infrared waves traveling outward from the flames. Convection has one fatal problem for a seated person. Warm air rises. It doesn't sweep horizontally across your torso in any useful concentration. What you actually feel sitting next to a fire, that warmth hitting your face and hands, is radiant energy moving in a direct line from the combustion zone to your skin. This is where one physics principle changes everything. Radiant heat follows the inverse square relationship. As you move farther from the source, the energy you receive doesn't decrease proportionally, it collapses. Move twice as far away, and the warmth arriving at your body drops to 1/4. Step back from 2 feet to 4, and 3/4 of your radiant heat vanishes. The math is brutal, and it works against anyone who builds a fire too large to sit close to. Now here's what this means for a bonfire. The problem with a bonfire is structural. Its sheer size makes it unapproachable without cooking the side of you that faces it. The fire's own structure forces you to stay back. You're sitting 8, 10, sometimes 12 feet from the main combustion zone. Every foot of that forced distance is costing radiant warmth at a rate the inverse square law makes brutal. A compact, well-built fire lets you position yourself within 18 to 24 inches of the combustion zone. Run the numbers, and a compact fire producing half the total thermal output of a bonfire, positioned 2 feet away instead of 10, delivers more usable radiant warmth to your body. The bonfire loses that comparison at the fundamental math level. Before we get to the structures that exploit this, lock in a quiz answer below. Radiant heat output from a fire stays constant. You move from 4 feet away to 2 feet away. What happens to the warmth your body receives? First choice, it doubles. Second choice, it triples. Third choice, it quadruples. Fourth choice, it barely changes. Use the quiz to record your answer. Now let's talk about oxygen, because controlling how air reaches the combustion zone is the single highest leverage variable in fire building, more than wood species, more than fire size. At its core, combustion is a rapid oxidation reaction. Fuel gases and oxygen collide at high temperature and release energy. Like every chemical reaction, it runs at the speed of whichever ingredient is in shortest supply. Cut off oxygen and you get sluggish, incomplete burning, lower temperatures, wasted fuel. Deliver oxygen precisely and consistently, and the same wood produces dramatically more heat. An open bonfire draws air from every direction around its perimeter, but the rising heat column creates chaotic circulation that disrupts delivery constantly. One section receives plenty, another is starved. The structure never stabilizes into a uniform, efficient burn. A fire built around a structured air channel operates on entirely different physics. The channel establishes a pressure gradient between the exterior air and the combustion zone, which pulls oxygen consistently toward the hottest part of the fire rather than letting it arrive chaotically from every angle. The fire transitions from drawing air in random, unpredictable bursts to receiving it in one steady, directed stream. That shift alone drives combustion temperatures substantially higher than the same fuel in an open configuration achieves. This is the principle behind what survival instructors call the Dakota hole, the most thermodynamically efficient open campfire configuration in documented field literature. The build is straightforward: 2 underground chambers roughly 18 inches apart connected at their bases. The primary chamber is the burn pot, about the size of a soccer ball, dug around 12 inches down. The secondary piece is a slanted air shaft bored from the surface at an angle to meet the base of the burn pot. As combustion gases heat and escape upward, they create a partial vacuum in the lower section. The air shaft becomes a passive pump, drawing fresh air straight into the base of the fire automatically. The process is self-sustaining from the moment the fire catches. No fanning, no adjustment required. What you get is a fire running substantially hotter and cleaner than any open surface configuration on far less wood. The Army teaches the Dakota hole partly for concealment, since most combustion happens below ground and the fire is nearly invisible horizontally. But the thermal argument is equally compelling. A burn pot no bigger than your torso in a properly constructed Dakota hole will outperform a sprawling surface bonfire built from several times the fuel. That's not an overstatement. That's directed combustion physics running as designed. Let's talk about the shape of the fire itself, because fuel arrangement is something most people never consciously think about, and it matters more than almost any other variable. Combustion happens at the boundary where hot fuel gases meet available oxygen, called the reaction interface. The rate of energy release is directly proportional to the active surface area of that interface. More combustion surface equals more energy per second, regardless of total fuel. A large bonfire has high surface area at its outer edges, but the interior becomes oxygen-starved as the fuel mass scales up. Wood at the center gets surrounded by heat, but cut off from the oxygen it needs. You're burning fuel on the outside and thermally degrading fuel at the core. A tipi-configured fire arranges fuel in a cone with the apex pointing upward. Every piece faces the hot core and the incoming air supply simultaneously. No oxygen-starved interior because the cone geometry allows airflow to reach every piece from the base upward. The structure burns evenly from ignition all the way to ash. The teepee shape also focuses radiant output toward a specific arc rather than spraying energy in every direction. A flat fire sends heat upward and downward, two directions that do nothing for the person beside it. The teepee concentrates that same output toward the arc in front of you. More of the fire's total energy captured by changing how wood is stacked before you light it. Now the fuel math. Dry hardwood contains a fixed amount of chemical energy per kilogram. The wood holds what it holds regardless of how you burn it. What changes completely is how much of that stored energy becomes useful radiant heat aimed at a human body versus smoke, convective loss, and infrared energy warming the sky above your campsite. A bonfire burning 10 kilograms of wood at 50% efficiency releases enormous total thermal energy. But the inverse square law, wide radiant geometry, and convective losses all compound against you simultaneously. The fraction of total output reaching a nearby person runs under 5%. The fire is massive, impressive, and mostly heating air above your head. A compact fire burning 2 kilograms at 85% efficiency tells a completely different story. You're sitting close, radiant geometry is focused toward you. Convective losses are minimized by the structure. The fraction of energy reaching your body runs 15 to 20%, 3 to 4 times the delivered warmth, 1/5 of the fuel consumed. By every measure that matters for keeping a person alive, the small fire is the correct answer. Second quiz question while you're thinking about it. One fire design listed below generates a passive vacuum that pulls oxygen directly into the base of the flames. Which one is it? The teepee configuration, the log cabin stack, the underground Dakota hole, or the traditional star layout? Lock that in before we keep going. One final factor most people overlook entirely: wind. A large open bonfire destabilizes in strong airflow. Cold air hits the windward face before fuel there can reach proper pyrolysis temperature, and the fire shifts and leans constantly. You have no meaningful control over it. A Dakota hole fire is almost completely immune because the combustion chamber sits underground and surface wind can't reach it. But here's where the advantage flips. When the intake tunnel faces into the prevailing wind, wind pressure increases air delivery to the combustion zone. The same environmental condition that weakens a bonfire makes a Dakota hole burn hotter. That is physics running in exactly the right direction. Reflective positioning compounds this further. A small fire in front of a rock face, a log wall, or a snowbank bounces radiant heat back toward you from a second direction. Same fuel load. Warmth arriving from two angles. A bonfire is too large and too distant to benefit from this meaningfully. A compact fire placed correctly delivers heat from two directions simultaneously, and anyone who's used this setup in real cold will tell you the difference is immediate. Stack all of it together. Higher combustion efficiency, inverse square proximity gains, focused radiant geometry, directed oxygen delivery, wind immunity underground, reflective surface capture. Every thermodynamic variable runs in favor of the small, intentionally built fire. There is no category where the bonfire wins if staying warm is the objective. There's knowledge that holds up in a physics textbook, and there's knowledge that holds up at 2 in the morning when you're down to your last 3 logs. The rarest thing in survival is when both give you the exact same answer. With fire, they do. Build smaller, build tighter, get close. The fire the size of your hat in a properly dug hole will outperform a bonfire every time the temperature actually matters.